Well, hello there. Today I will be talking about Zorg-KRW conjecture. This is joint work with Alexander Small, and let's get started. So, this work concerns the lower bounds for Demorgan formulas. So the Demorgan formula is just a tree that computes a function by applying AND and ORs to the literals. I hope you're familiar with that. So the depth of a function is the minimal depth of a formula that computes this function. And our holy grail is to prove that P is not equal to NC1. And to show that, we need to find a function f that is in P and that has a super logarithmical lower bound on its depth. All right, so one approach to do that was proposed about 30 years ago is the Krw conjecture. That says that if you take two functions and you compose them, meaning that you take your inputs and dissect them into blocks, and then you apply G to every block, and then you apply F to the result. Then you will get this like new composed function, and the KRW conjecture claims that the depth of this composed function is roughly equal to the sum of the depth of the functions. I know this roughly equal may not seem the most mathematical term, but the thing is there are many different ways you can define this conjecture, but with different meaning behind this roughly equal thing. But they all share one thing in common. They all imply that P is not contained in NC1. So yeah. Because it's hard to talk about formulas, we decided to focus on Krw games, right? So this is just another language to talk about complexity of the functions. So Krw game is Alice is given an input such that the value of the function is 0. Bob is given the opposite, the input that the value of the function is 1, right? And they need to find a bit of a difference where the inputs, the bit of the difference. So clearly the inputs that are given to them are different, because otherwise the value of the function would be the same. So yeah, that's the Krw game for the function f. What's so nice about it is that the protocols for the deterministic protocols for the Krw games directly correspond to the formulas for those functions. So instead of lower bounding the depth of the formula, we can just lower bound the amount of communication needed for the Krw game. And then we can just reformulate the KRW conjecture by saying that instead of composing functions, we can just focus only on communication complexity and have the composition of games. The complexity of the composition of games should be roughly equal to the complexity of the composition of, just roughly equal to the sum of the complexities of the games. All right. So how do you solve a composition of Krw game? So you have your input, which is this matrix X, and you apply a function to it, and you to every row, and then you get a vector, and then if you apply another function to it, right, you get a 0, and for Bob it's other way around. So he has a matrix, and he applies G to it, to every row gets a vector, and if he applies a function to that, after that he will get 1, which is different from 0. So they need to find a bit of a difference between matrices, and well, there is an obvious way just by sending the whole matrix, and then Bob can find a bit of a difference, tell it to Alice. But obviously there is a better way to do this. We can just first solve the Krw game on the vectors, right? So we can find a bit. So this bit here, right? So for example, here can be 1 and here can be 0, or other way around. And then we know that the value of the function g applied to the rows of the matrix would be different. So we can solve the Krw game on the rows and find a bit of a different on that. So instead of thinking in terms of formulas, where you would think from the bottom, right? You apply G to the inputs, and then you apply F at the results of the inputs. Here we have this like top-down thinking that first you solve one game that is f, and then you go to the actual inputs and solve another game. All right. So because it's hard to us to talk about functions, we have this universal relation. It was defined to be this like mother almighty Kashmir-Regression game. So you can think of that as if Alice and Bob are trying to solve the Kashmir-Regression game, but they just don't know the function. It was not given to them. So Alice and Bob are both given an input, and they need to find a bit of a difference. And instead of having a function to separate them, they just have a promise that their inputs are different. And of course, this is a hard relation. You need at least n bits of communication to solve it. By reduction from equality, for example, that can be easily proven. But where things are getting interesting is when we're talking about compositions of universal relations. So because we want to solve the Kashmir-Regression conjecture, we need to talk about compositional functions. And it's hard, so okay, what is this like model object? So again, this is just like compositional functions, but we have like basically things that Alice and Bob just don't know the functions that they applied to the matrix to get vectors and to the vectors to get different values. So to have those properties, we first need that A is different from B. So it actually defines some Kashmir-Regression game. And also, if the values of the vectors are different, and I remind you that the vectors, like, they're supposed to be the results of applying some function to the rows of the matrix. So if the values of the vectors are different, that should imply that the corresponding rows of the matrices are different. So that kind of, to get the same feeling that we are working with compositions of functions, but without functions. And we can apply the same strategy to get the upper bound, right? So we have, now we have this like matrix and a vector on one side, matrix and a vector on the other side, and the only thing we know that vectors are different. So how can we solve that? Well, we just do the same strategy. We first apply solve the Kashmir-Regression game on the vectors and get the bit of a difference between A and B, which implies that there is a bit of a difference between corresponding rows by the properties of our problem. So we can just solve another universal relations on the rows. So we get the desired lower bound, the desired upper bound. So what about lower bounds? So what is first, let me talk about what are we doing here. So instead of talking about the standard Kashmir-Regression conjecture, we propose our own variant called the Zorg-KRW, and we were trying to replace the standard block composition with something that will give us a little bit more grip, right? To kind of entangle the inputs a little bit more. So the idea was to apply the functions with that outputs multiple bits to every row of the matrix, and then XOR them all together to get the vector. So that every bit of the vector depends on the whole matrix. But it turns out that you don't need the whole power of that to prove what we are trying to do today. So instead I will be talking about only the weak Zorg-KRW conjecture, and if you're interested in more details about the general version, please check the paper. But yeah, so the Zorg composition, we have two functions. One is from n bits to 1 bit, the other one is from n bits to n bits, and we have this Zorg composition where we just apply f to the entry-wise XOR of x and g of y. So it's rather simple construction. So we significantly reduce the size of the input. Not that it was an issue before, but it's just a lot easier to reason about this thing. And because we can still prove lower bounds, it just boils down to a very simple kind of dichotomy of what to do. So what is the conjecture? Our version is here, right? That for every function, there exists a function g that f composed with g is just harder, significantly harder than the original function f. And in this form of the Zorg-KRW, it also implies that the traditional block composition is also hard, right? So if we just composed f with some function h in the standard sense, it will give us also this function that is harder than the original one. So, all right, why should you care? Because this version of the conjecture does not imply that p is not equal to NC1, but the general one does, but we'll focus on this one, and the motivation is that the whole approach supposed to prove p not equal to NC1. So my feeling is that it's supposed to prove some lower bounds on the way before we actually get to the whole super polynomial lower bounds. So how about we'll just try to prove n to the 4 or n to the 3.001 lower bound on Demorgan formulas. So just let's baby steps, right? So let's scale down our ambitions a little bit and prove something very concrete. And so if we can prove the Zorg-KRW not for depth but for size, right? So that if you composed f as g, then the size of the function would be a little bit better than a little bit bigger than the original function f by some like exponential factor. Then this would be enough to prove the lower bound for this modified Andreev function, right? So then we can modify Andreev function to work not with just one function, but with a composition of functions as a core. And this is the same proof we'll just go through, and we have this n to the 3 plus epsilon. So the whole idea is that Andreev function the proof for Andreev function only needs the existence of a hard function in a rather small set, and that's exactly what is proposed by the Week's Zorg-KRW. All right, so this is the motivation. Just we'll try to prove n to the 3 plus epsilon by thinking in this direction, but unfortunately for now I cannot provide you with answers for that. So let's see what we know so far. So the first two papers by Edmonds and Pagliazza, Rudish-Skal, and Hassett and Widerson proposed two different ways to prove that composition of universal relations required 2n bits of communication. Then there was this breakthrough like 15 years later, right, that composition of a function with a universal relation requires quite a bit of, right? So this is basically the depth of the function f, right, up to a small factor plus n. So you can think of that as just the depth of the f plus n. And in some sense, this is actually just better, right? So what we are proposing in this work, we're saying that there exists a function g such that the flipped version, where we're composing universal relation with a g either in a block way, traditional one, or in this like Zorg composition that we are proposing. So both require 1.5 n, so better than just universal relation on its own. And let me tell you why I'm so optimistic about this whole affair, because the first result by Russell and others was that composition of two universal relations, it was proven by maintaining symmetry. So you go down the protocol, and what you're trying to do is to maintain as many possible inputs that can be given to both players. And then after like n bits of communication, you say like, hey, there's still like parts of the matrix that we haven't talked about a lot. So what we do, we force players to find the difference between those rows, and we show that still takes like roughly n bits of communication. I'm a little bit misrepresenting the argument, but the philosophy of this is, the idea is that. So, all right. Then there was this amazing work that composed a function with a universal relation, and it was proven by providing this measure argument. So the idea is that you find a measure of a rectangle that doesn't go down too fast during the communication, and then you show that this measure is large at the beginning of the protocol, at the root, and then you show that it's rather small at every leaf, which obviously proves that there are many leaves in the protocol. Okay, so and the whole work here is to find this measure. It's really cool measure. I just really like it, and it's hard to come up with it, and it's I really like this proof. And then the whole thing is to actually prove that this measure is upper bounded at the leaf. That's where the whole work is going. But yeah, I'm not talking about that paper here. But my argument is that our proof for UN composed with G is done by a symmetry argument. So one can hope that by substituting the symmetry argument with the good measure, you can do the same thing for composition of F and G, right? Because symmetry argument is basically just a very simplified measure argument. It's the idea that the number of inputs that can be given to both players in a rectangle is basically a measure. Well, it is a measure of a rectangle, and then what was done to prove composition of F with G, F with universal, is that they replaced this symmetry with something like that, but that works for all rectangles, not just squares. And we need something like that here, and just, the main takeaway from this talk is go do that. That seems like a very nice direction to work. Just can we combine those two techniques to work together? All right, so let me go to the actual details of the paper. So first of all, you might have noticed that in our proof we have this existence of G rather than for every G, and this is not something that can be fixed, at least in our approach. So, and the reason for that we don't really work with any particular function. We work with this multiplexer kind of games. So the idea is that because we don't know how to define a hard function, we will define a game that kind of encapsulates all the function in it, and then try to prove lower bound on that, and then extract the lower bound from for the concrete function out of this multiplexer thing. So Alice is given a function and an input, and the value of the function on that input is 0. And Bob, I'm sorry, that was supposed to be f. The value of the function is of f of x is 0, the value of g of y is 1, and they need to find a bit of a difference, or they can output this error symbol if f is not equal to g. And this would be our main objective, right? So to extend that to a composition, we propose this composition of a function with a universal and a composition of a multiplexer with a universal, right? So the first one it's kind of what it is, right? You're given two inputs, and again, we don't have a function f, so we just have this if our values are same, right? Then output the error symbol. Otherwise, you need to find a bit of a difference between x's or between y's, and we don't want to do that directly. So we propose this multiplexer version, right, where both are given functions, and they either need to find a bit of a difference here, right, or they need to say again, like that the universal relation part is bad, right? That what we outputting is actually equal instead of rather than non-equal, which was supposed to be the correct thing for universal, or we have that functions are different. That's kind of a problem to extract the existence of a hard function from the multiplexer. It was done for alternating communication, and it was done for the normal with some some factor. Oh, yeah, so we're losing some of the complexity on that, but our solution here is to go to the half-duplex communication. It's basically a normal communication, but Alice and Bob can do whatever they want. It's chaos. They can send, they can listen. So if they can both try to send to each other, and then nothing will happen. They can, of course, one send, one listens, and then it's just a normal communication, or they can listen and then just some adversary give, so they just hear some noise, right? So they don't know if it's noise that is coming from, that's like the symbol that they're getting is coming from the other player, or it's just some random noise. So they have to be prepared for that. Right, so yeah, it's defined just as two protocols rather than just one. And we know that for any function, the normal complexity is at least as large as half-duplex complexity, and then the other way it works with a factor of 2. The cool thing is that we have our lower bound for equality, which is like n over log 2.5, which is non-trivial, right? It doesn't follow from those simulations. So yeah, what do we know about this half-duplex thing? So first of all, we have that equality is hard on any set, and then the main reason why it was introduced is that if we have a half-duplex lower bound for multiplexer, it immediately implies the existence of a hard function. So how do we do this? Suppose that all functions were simple, then Alice and Bob can just start the best possible protocol for their function. And then, because in this world of half-duplex complexity, you can do whatever you want. You just both follow your own protocol, and then you verify the answer on, or you report the error symbol. And this proof doesn't work in normal complexity because suppose F and G protocol for F and G were both starting with like one was starting with Alice sending a bit, and the other one was starting with Bob sending a bit. Then what we're describing is not quite the protocol, so you just cannot do that. But in half-duplex world, you can do that, absolutely. So then you have this partially half-duplex, which is just another spin on the same idea that it's a half-duplex, but it only actually doing something non-classical if f is not equal to g. Its model is specifically defined to work with multiplexers, so it only makes sense for them. And we have the same lemma, and the proof is absolutely the same. So the only difference is that we can actually prove a much better lower bounds for partially half-duplex models. All right, so here is how we're doing this, how we can prove existence of a hard function. So first of all, we need to prove that the multiplexer requires n bits of communication, and we're doing this by reducing the non-deterministic communication complexity of non-equality on the strings of size 2 to the n to the multiplexer thing. So that makes sense, right? The size of the functions in the multiplexers are like 2 to the n, so the size of the inputs are they do make sense, right? So the main idea that if we find like this non-classical round, that's already proof that f is not equal to g. So we are guessing the transcript, right? And then like we also need to prove to guess how long it is and what is happening at the end of it. And either the transcript defines a classical protocol, or they can find the non-classical round after the protocol, after the transcript. So either they go into this error symbol, which is the proof that f is not equal to g by the definition of the multiplexer, or they find the non-classical round, which is also the proof of f not equal to g by the definition of the model. So this is just a proof that like a non-counting, kind of non-counting proves of existence of a hard function. So how do we prove the lower bound for the the composition of a universal multiplexer? Well, this is again the definition, and then first of all you reduce it to a sum square, just to weed out some undesirable inputs, and then again, the first stage, as I mentioned, we work in two different stages. So the first, you go down the protocol and you say, hey, the size of the intersection doesn't go faster than 2, like it's reducing not faster than by a factor of 2 every round of communication. And then, so the main technical lemma is to say that if we have a rectangle that was produced by the first stage, then in the intersection between two inputs, there are either ways to fix y and j such that there are a lot of different x's that can be given to both players, right, with those y and g, or we can find a set of functions of this like gigantic size such that any two functions are distinguishable. That's the word. So first of all, that there exist an x and y such that x and y can be given to the players with a g, with their g, and also that g's of y are different. All right. So here is a sketch of the proof. So first of all, just go down the protocol like n minus 3 rounds and just pick the node with a large intersection. Then there are two different cases, right? First of all, we have this giant set of axes that can be given to both players. That should be y. All right. And then we can force the player to solve equality on that set by just simply fixing g and y on their side, just wearing the x, and that will force the player to solve the equality problem. So otherwise, you have this gigantic set H, and what you do, you can show that you can use the protocol to solve the non-equality non-deterministically on H. And if you work out the math, that would actually give you the right number. So this is a proof that it requires 1.5 n minus something small. All right. So how do we extract the lower bound? Well, we do that in the half duplex world. And the first stage, we're doing something like, so we can show that the measure is not going down too fast. In the classical communication, it was going down by a factor of 2. In the half duplex communication, it's not going down faster than 2.5 every round. So so we can prove this horrifying number of rounds is needed for the problem to be solved, so which sum up to this 1.006 n. And then we can use this reduction from half duplex complexity of multiplexer to a normal complexity of a function to prove the lower bound 1.006 for some function g. Yeah. So how can we do better? We can focus on this partially half duplex communication and prove actually 3 over 2n lower bound in the partially half duplex world. It's a little bit more complicated, but it can be done, which immediately implies the 1.5n for some function. So, yeah. What are some of the open questions? First of all, our ways to convert lower bound for the classical communication into half duplex is rather like ad hoc, right? So every time we need to do something, some work to actually reprove results in a new model. So is there just a generic way to do that without losing a factor of 2, of course, right? So can we actually prove that any lower bound in classical communication can be just immediately turned into lower bound in partially half duplex, for example, or if it can be done by, like, if the proof has to be in a particular form, then it can be done. That would be really nice and really, simplify our future work. Then, okay, can we prove the better lower bounds 2n for UMN in any of the models, preferably half duplex, but or even partially half duplex? That would be really nice. And most of all, can we actually prove that composition of two functions is hard for some function f and some function g, that would be enough to prove, it would be almost enough to prove that under a function require 3 plus something. Right, so proof supercubic lower bound. So that's it. That's what I wanted to share with you, and thank you.